Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Fundamentals of Nano and Quantum Photonics. So today onwards we will shift gears. So first 8 weeks we have been talking about nanophotonics, and now we will start talking about the quantum aspects. Okay, and more specifically today we will talk about, or in this week we will talk about photon statistics. How do we distinguish classical light from the quantum light? Okay, we will try to understand what this is. So the motivation is this. So if you look at optics classically in the 60s and 1600s and 1700s and so on, the lenses were made, optical systems were relatively bulky, and the waves would propagate through that. So we can think of classical optics as being, a regime where the intensity of the light is large and the size of the devices also is relatively large. Okay, we have done this for at least 250 to 300 years or more. Okay, now we talked about in the first 8 weeks of the course a regime where we tried to shrink the size of the device. Okay, this is basically we went from large sizes, we went to nanoscale devices, and that we called as nanophotonics. Okay, we understand various aspects of it. Now in the same, in the last 30 to 40 years, there has been another direction which was investigated in the optics community. That is to move from classical optics to quantum optics. This happens when you reduce the intensity of light, so lower intensity. When you reduce the intensity of light, you move into a regime where there are just few photons, and then you can understand and study the properties of few photons. That is the quantum optics. And I believe that personally the next 15-20 years of research is going to be in the realm of quantum nanophotonics, which combines both, the smaller size and the lower intensity. So this is probably where a lot of research will happen in the next 15-20 years. So the main difference from the classical optics, and the difference between the classical optics and quantum optics, is that in classical optics we deal with light as an electromagnetic wave. Okay, the wave has a particular amplitude, it has a phase, and so on. Now when we come to the quantum optics, we deal with photon as a particle, right? So it's a quantum of energy, and the idea of photon itself is quite deep. And my advisor used to have this quote. So the quote is from Einstein. Apparently, towards the end of his life, Einstein said this. So all the 50 years of conscious brooding have brought me no closer to answering the question, what is a light quanta? Of course, today every rascal thinks he knows the answer, but he is deluding himself. The idea is that the idea of a quantum of light is a very deep one, and we are still understanding it. There are various interesting aspects to it. Okay, so we will try to understand some aspects in this course. All right. So the story starts with the study of blackbody radiation. In the mid 1800s, a lot of people studied how light is emitted from a black body. Simply, a black body is something that is perfectly, it doesn't reflect at all. It has zero reflection, so it's essentially black, and all the energy is confined. Let's say you take one such ideal black body. It may be a box which is painted, and then you heat it up. And they make a small hole in that so that energy will escape. So what kind of radiation will you see? That's a question. Okay. And they studied various heated objects, and they found out that the energy is emitted in a characteristic way wherein at long wavelengths you have small emission, and as you increase in the frequency or decrease the wavelength, the emission increases. One of the most famous examples of a black body is a sun. Sun has a temperature of 5000 Kelvin. Let's say if I take an object and I heat it up to 5000 Kelvin, it will emit radiation which looks similar in profile to what sun does. Okay, so that's why we call it as a black body. And we see that, we only look at a very small portion of the spectrum here. Maybe this is only visible spectrum, 300 to 700 nanometers is what we see. And the whole evolution happened. Why do we see in the visible wavelengths? Why don't we see in the IR? It's probably that the reason is that sun has the highest emission in the visible, and that is why all the plants and organisms evolved to actually utilize that particular energy. Maybe if the sun has a lower temperature of only 3000 or 2000 or something like that, lower temperature, then maybe all of us start looking in the IR. I mean, it could happen anyway. So the whole, so people knew this for a long time. They have studied black body radiation, but they had a problem explaining it. The issue was, if you look at the classical theory, let's say I'll take a box of this form and I'll try to study how much energy it radiates. It radiates energy because you excite certain modes in that. Okay. What are modes? Well, I have a box like this. I could have a situation where there is a wave pattern which is like this. Even number of wavelengths, or integrated number of wavelengths. You can have some modes, or you can have higher frequency modes and so on, right? You can have various modes in this. Just like, what you see on a guitar, right? You have a certain length and you have a string, it has certain modes. If you press it, you pluck the chord, essentially you are changing the resonant wavelength and you are changing the sound that is emitted from there. So when you have such a scenario, they applied this theory. They calculated using very detailed analysis. They figured out that the density of modes here is proportional or equal to omega square by pi square c cube. This was the density of modes. I think I mentioned this in the context of electromagnetic waves, but this is it. Yeah. 1 second. Yeah. All right. So you have the density of modes which is given like this. You can calculate this from basic principles. Now, classical theory tells us that each mode is indistinguishable, and if it's a temperature of T, the body is heated to a temperature of T, it should have an average energy per mode of K times T. Mode is equal to KT. So this theory tells us that if I have a black body radiation, I should see that the total amount of energy, which is essentially the radiated intensity, is going to be product of these two, the density of modes times the average energy. And now you see that the density of states is increasing as omega square. So as you go to lower wavelengths or in higher frequencies, the classical theory tells us that the amount of radiated power should be increasing. So this is my classical theory. This is a problem because how do we explain this? In experiments, we don't see this. We see that the radiated power is actually reducing at short wavelengths, and that is not predicted, and it was called as ultraviolet catastrophe, and this is one of the key points that led to the discovery of quantum mechanics, okay, in trying to answer this. So how do we answer this? So answer was actually provided by Planck. Planck postulated that the energy emitted by a black body is not continuous. In the classical theory, there is nothing that tells us that it is, it should be continuous. But he said that no, energy is going to be quantized. And the quantum of energy is going to be equal to E is equal to H cross omega or H nu, both are same. So he said that light cannot be emitted or energy cannot be continuous, but it's a discretized thing, which frequency and H bar. Okay, light can only be emitted or observed in those quanta. Okay, later on, I think a scientist by name Lewis gave the name of photon to it, but he just considered that energy was quantized. And with that assumption, Planck derived average energy per mode. And he found out that the average energy per mode is the quantity that I have already written here. So this is my average energy per mode. So what this tells us is the density of states is same. You have the same omega square by pi square c cube dependence, but the average energy reduces as you go to higher frequencies. So as you go to higher frequencies, this exponential term increases. So 1 over that should reduce. So the average energy reduces, and that's why you see that the radiation intensity is this form. And Planck's theory was able to accurately capture the black body radiation, and that's why idea of light quanta became accepted as well. Okay, so this is the origin, light quanta. But what do we do if we want to study the quantum of light? How do we do that? For example, we could think of an experiment wherein I'll take a light beam. let's say I'm considering a light beam at 620 nanometers. So if I consider lambda is equal to 620 nanometers, and let's say it has a power of 1 milliwatt. Okay. Now we understand that there is this light beam which is incident on a detector. This is basically a detector. When you have a detector, let's say there's a photon that is incident and it generates one pulse. And how do we study the quantum nature of light? By looking at how the pulses are. This counter can actually give you an output which is count rate. It tells us how many photons are incident per second, let's say. We want to do that, so it generates some sort of a electrical output which is schematically shown as this pulses. By looking at the pulses, I can know that okay, there is a photon that is incident. So what will be the count rate that we can expect in this case? Okay, the power is given to us as 1 milliwatt. So my power is simply nothing but energy per time. So P, energy per unit time, and that's basically what is energy. The total amount of energy is going to be simply the number of photons times h nu divided by time. So with that we can define a quantity which we call as photon flux, and I'll represent it by phi, and that is going to be simply power divided by h nu. Okay. So what will be the units of my photon flux? It's going to be number of photons per unit time per second. Okay. Units is, sorry. So what will be the photon flux that I will see when I have a situation where this wavelength of 620 nanometer light is incident. So now my power is immediately there already. So power is going to be 1 milliwatt divided by h nu. What is h nu? Well, you have to calculate. So we want to, we know this because, we know that 620 nanometers corresponds to 2 eV of light. Okay. So I'll basically, milliwatts is joule second. So I'll maybe write it like that. It's 1 millijoules, right, per second, divided by h nu is going to be 2 eV. So 2 into 1.6 into 10 power minus 19 joules. So with that I can compute how much will this turn out to be millijoules. So 10 power 3 point something. So it will be something like about approximately 3 into 10 power milli, right? So 10 power 15 photons per second. This is my flux. Okay. Now can I detect this 10 power 15 photons per second? If I have, this is the typical power that you will have when I have, let's say, a laser pointer. It has a few milliwatts of power, and 620 roughly could be a wavelength at which that laser is emitting. So will you be able to study the quantum properties with this laser? No, it's not possible. The reason is the detector is never going to instantaneously measure. Rather, it takes certain time. It can detect one photon. One photon is incident. It can generate an output pulse, but then it cannot immediately detect a second photon. There is something called as a dead time. Okay. So the dead time is essentially the time period in which a detector cannot detect a second photon. Okay. So the detector dead time typically is about microseconds, 1 microsecond, let's say. So that means one photon comes. If a second photon comes within 1 microsecond, it cannot detect. That's a typical number for the most detectors right now. So the practical count rate is going to be 1 over that. Typically you can do 10 power 6 photons per second. That's what you can do. You can't detect more than this. But now we saw that here 1 milliwatt of beam has a count rate of photon flux of 3 into 10 power 15. How do we overcome that? So 1 milliwatt at that wavelength, of course, has 3 into 10 power 15 photons. If you want to reduce it to practical limits, I'll have to go to something like 1 picowatt. And that will give me 3 into 10 power 6 photons per second. Okay. So now this tells us that if you want to study the quantum properties of light, we have to work with extremely low intensities. And this is one of the reasons why I showed you in the initial graph, on the x-axis we had the intensity. I said that we have to go down in the intensity. Okay, that is because you don't have any practical electronics that can actually detect this. Okay, of course, when you are dealing with picowatts, if you shine a picowatt beam, probably you will not even see it easily. Okay, so we'll have to have specialized detectors for that, and these are called as, one of the popular variants is basically what is known as a PMT, which is simply photo multiplier tube. So basically this is a detector which is held at a very large bias, and one photon actually leads to a cascade, an avalanche ionization process, and then a lot of electrons are generated and it generates an electrical output pulse. That's one class. The other class are known as avalanche photodiodes. Okay, avalanche photodiodes. So basically these are reverse bias junctions, and you shine light and then they create electron hole pairs, and those electron hole pairs accelerate because of high voltage and create secondary electrons and so on. Eventually you generate a large enough pulse. Because that avalanche process takes time, you're going to have a certain dead time associated with the detector. It can't immediately detect. Sorry, there's a question I believe here.
Can we not play with the dead time?
Okay, the question was, can we not play with the dead time? Can we not reduce the dead time? Right? Of course, we would like to do that. But finally, you see, if you are taking, what is the energy of photon that you are trying to detect? Even if you take 2 eV, 3 into 10 power minus 19. So it's very, very joules. It's a very, very small amount of energy. A laser, for example, can you detect a laser? Let's say you want to detect the laser. I'll take a laser pointer and shine it on your hand. Will you know that you are actually being hit by a laser pointer? A laser pointer has 1 milliwatt of energy. That means 1 millijoule per second. You're not able to even feel it. 1 millijoule per second is a small quantity of energy. Right? Now, if I hit you with 1 photon of that. So instead of 1 millijoule of energy, I'm talking about 10 power minus 19 joules. There's no way. I mean, it's like, what? I don't even know what 0.1 attojoules. Right? 0.1 attojoules, can you sense it with your hand or something? It's very, very difficult. You need an extremely sensitive detector. So if you want to have such a detector, the only way to actually go around that is by using the avalanche process or the multiplication process. So what happens in an avalanche diode? You have a large field region, and then you have an electron hole pair which is generated, and the electron go in one direction and the holes go in the other direction. They acquire high speeds, and the energy is basically they knock off further electrons. Secondary electron hole pairs are created and so on. So that process takes time. You have to build up that from a single event of very, very small energy. You have to build up a large enough signal. That takes time. So the origins of this is in the gamma rays and all that. If you think photons are difficult to detect, how do you detect gamma rays? So people have built detectors for that. All these Geiger counters and so on, right? They have a lot of studies have been done with these photons. Okay, but it takes a lot of it takes time. It requires specialized equipment like this, photodiodes and photomultiplier tubes and so on. Yeah, does that answer? Uh-huh. Uh-huh. Mm-hmm.
When you look at the final expression,
Mm-hmm.
you don't see any, when you look at even particle in the box, you see quantization is the end term coming,
Mm-hmm.
So why don't we see any of it? Looks still like continuous.
Okay, that's a nice question. So the question was, Planck, we say that Planck considered energy to be quantized. So we don't see any expression for n. Like for example, if you take a particle in a box, in energy you see that, n square, pi square divided by L square into whatever, k square h cross k square, right? That's what the expressions we have, particle in a box. Where is the n term to indicate that it's quantized? Well, the thing is, if you look at the black body radiation, I mean, it's a nice question. It turns out that the number of photons or number of photons in this mode is given by this expression, number of photons in a particular mode is given by this expression 1 over exponential h cross omega by kt minus 1. This is the expression for number of modes. So I'll later, at one point I'll use it again. So this basically captures the number of photons. So, and then the average, the energy of the photon is h cross omega. The number of photons is that. So product of that gives you the average energy per mode. So it's all built in, and it turns out to be very tiny. I mean, you can actually do this experiment. The density of modes is something, right? Omega square divided by pi square c cube. So that's the density of modes. You can compute how many modes are there in a particular volume. Okay, and from that you will see that it's huge number of modes. Yeah, and the energy is quite small. That's all. I mean, you can also think about it in terms of wavelengths, right? You have to go to very, very tiny volumes where you'll see the number of, the number of available modes reduce. Because this is the number of modes per unit volume. Omega is what? In terms of 10 power 14 square, 10 power 28, right? 10 power 28 divided by c cube is 24. 10 power 4 modes per meter cube or something like that. So it's a large number of modes that are present, even in a tiny volume. We'll have to really go down to levels, nanoscale levels, to see some effects. I mean, in fact, actually, this is what we already know, because I talked about the Purcell effect. This is the density of modes in the free space. The moment you have a nanostructure, we are playing with the density of modes. That's what, the increase in the density of modes in the nanostructure is called Purcell factor compared to free space. Yep. All right. So, so we understand. So we'll have to go to low levels. Okay. So I'll just take a few minutes and then solve a couple of problems so that you are more familiar with this concept. So basically the first problem I want to look at is, let's say there's a beam of energy 1 eV, okay, beam of 1 eV light with an average energy of 1 nanowatt. That's incident on a photodetector with eta. Eta is basically the quantum efficiency. I didn't mention it before. So this is my quantum efficiency. I'll talk about it, what it is. So we have this. So calculate the average photon flux and count rate. So what is the photon flux? We know that photon flux is simply going to be phi is power divided by h nu, right? If you have 1 eV light, we know what is the energy of the 1 eV light. So power is now 1 nanowatt. So 1 into 10 power minus 9 nanowatts, sorry, 10 power 9 watts. And then energy is going to be simply 1 eV. So 1.6 into 10 power minus 19 joules. This is joules per second. So that is going to be turning out to be how much? 1 divided by 1.6. It's going to be something like 6.25 into 10 power 9 photons per second. Okay. That's typically what it is, right? I mean, that's what we calculated. If you have a 1 milliwatt of 2 eV photon, we said it's going to have 3 into 10 power 15. So we come down to nanowatts, that's 10 power minus 6 reduction. So the photon count also reduces. Now it's instead of 2 eV, 1 eV photon. That's it. So it makes sense. Now this is the number of photons. But how many electrons will be produced when this number of photons are in? A perfect photodetector will give you equal number of electrons. But that may not be possible. Or equal number of electrons or equal number of pulses, let's say. Okay. The count rate that you detect after a detector in the counter, right? I can call it R, and that is going to be some fraction of it. Eta times phi. Phi is my photon count or photon flux. Okay. Phi, this is my photon flux. You have that number. This is my quantum efficiency. Okay. So your quantum efficiency has to be very high. Already we are dealing with very low photon count. Your quantum efficiency should be very high. are necessary. Only then you will see the quantum properties of light. Okay. I'll also talk about laws, how it impacts in a moment. But yeah, in the next lecture maybe we'll talk about laws. Next lecture. Yeah. All right. So let me take another example here. Instead of this, what will happen if you have a pulse laser? This is a continuous laser. Let's say instead of this scenario, I'll have a case where, let me simply change it up, and let's say that I have 800 nanometer light, and then that also has, let's say, 1 milliwatt power. Power is 1 milliwatt. But this time, instead of a continuous laser, it is a pulse laser. Okay. Repetition rate of 100 megahertz. That means it generates 10 power 8 pulses per second at that average power of 1 milliwatt. So what will be the number of photons? Average number of photons in this case. How do we compute? So basically power is energy per unit time. Okay. Now how many pulses are there? 10 power 8. So your power is going to be energy divided by time. Time is in this case into frequency. If I do repetition rate, I'll get the time, right? So energy times rep rate times the rep rate. So my energy per pulse is going to be 1 milliwatt divided by 100, or rather 1 into 10 power 8. Right? Am I making a mistake? I hope not. So this is going to be 10 power minus 11 joules energy. So how many photons are present in the 10 power minus 11 joules? How do we do that? The number of photons, average number of photons is going to be energy is 10 power minus 11 joules divided by the energy per photon. How much is energy per photon? In this case, wavelength is 800 nanometers. So we know that EV basically is going to be 1.24 divided by 0.8 micrometer. That is how much? 1.24 divided by 0.8 micrometer? 1.5. Actually, it will be 1.55, let's say. 55 EV. 1.55 or 1.55 EV, okay? Okay. So basically, this is the energy of photon. So basically, 1.55 goes into 1.6 into 10 power minus 19. So if you do that, some number will come. 10 power minus 11 divided by 10 power minus 19. So the 10 power 8. 10 power 8, 10 power 7 to 10 power 8 photons per pulse, because energy per pulse. So it is this. So we said that previously, in the previous case, when we consider this, we said that we have 10 power 6 photons per second, right? If you want to reduce, if you are working with continuous wave beams, you can't do much. You have to go to very low powers. If you want to still work with 1 milliwatt of laser, right, then you will have to make a very short pulse. Okay. And you have multiple, you don't have a continuous beam, that will reduce the number of photons. That's another way of reducing. Right? One is cut down in intensity or cut down in the time period for which the pulse is on. Okay. But these are the essential techniques to create, to study quantum properties. Okay. Any questions? All right. So let me just do one more problem in a different way. The same thing, but in a different approach. Okay. So now you are asked to consider the same problem. I don't know why we are asking the same problem, but yeah. Let's say, okay. The difference is that calculate the average number of photons. Okay, this should be in a beam segment of 30 centimeters. Now the question is, the photon flux we know. Because it's 1 EV photon, it should be something like 6.2 into 10 power 15 photons. Oh, it's not, this is nanowatts beam. So 15, so 10 power 9 photons per second. Okay. You have the flux. Now the question is, how many photons are there in a 30 centimeter segment? So if I take a segment of this form, let's say there's a block like this, the length of this guy is going to be 30 centimeters. How many photons are present? So we know that the speed with which they pass is basically 6.2. So 6.2 into 10 power 9 photons per second. So 1 nanosecond, how many photons would be there? If I take per second 10 power 9 photons, so 1 nanosecond will have 6.2 photons. Okay. And how many nanoseconds is 10 centimeters? How do we know? 10 centimeters, how can you, we can talk in terms of the time, right? So basically speed of light. Speed of light tells you the distance divided by time. So if you want to know how much is the length, means C into the nanoseconds, right? This length L is going to be 3 into 10 power 8 into 10 power 9 minus 9 nanoseconds, right? So that's going to be 0.3 meters. That's going to be 30 centimeters. So if I have a photon, so basically now question is, previously we said, okay, how many photons are there in a particular time period? Now we are saying in a segment of 30 centimeters, how many photons are there? And the answer is going to be, how much? 6 photons. So essentially, if you, and if I change up this problem a little bit, and I say instead of 1 EV photon, I'll consider 2 EV photons. Okay. If I consider 2 EV photons, in a nanosecond, how many photons would be there? In a nanosecond, if it's the same milliwatt, nanowatt of energy, 1 nanosecond will have 3.1 into 10 power 9 photons per second. Okay. Simply energy is in the denominator, right? So basically, if you reduce if you increase the energy to 2 EV photon, then you'll have lesser number of photons. So 3.1 photons. And if you have a 30 centimeter segment, you'll have 3 photons. 1, 2 and 3 photons are in that segment. Okay. Think about it. 30 centimeters is this much. And you are dealing with just 3 photons in that time period and you want to detect that. So it's an incredibly challenging problem that has to be dealt with. Okay. So this, I hope, gives you a glimpse of what we are dealing with when we come to quantum photonics. Okay. So we'll have to go down in low intensities, or we have to go to very short time scales, okay, where we are dealing with few photons. We cannot deal with a 1 milliwatt beam, laser beam, continuous beam, which has 10 power 15 photons. If you have that many number of photons that are coming, there is no detector that is available that can actually respond to that at that speed. So we cannot study it. Okay, so we'll have to deal with low light intensities. Okay, this is one of the reason, practical reason. Slowly we'll also talk about how the quantum properties of nature will be affected with the number of photons. Okay, so we'll talk about the statistics and we will we'll do that in the next lecture. All right. Any questions? All right. So thank you so much. I'll stop this and I'll see you in the next lecture. Take care.